Is zero-carbon steel truly a perfect solution? Not quite. Welcome to the 14,400 mJ energy bill that caught 53% of students off guard. Steel is an essential component of modern life. In 2023, approximately 1.9 billion tons of steel was made worldwide, and steel production was responsible for 8% of global carbon dioxide (CO2) emissions. In traditional steelmaking, iron ore, which is primarily iron 3 oxide, Fe2O3, is reduced with a form of carbon, C, known as coke. This occurs in a blast furnace with temperatures between 2200 degrees C and 2300 degrees Celsius, producing molten iron, Fe, and forming CO2 as a byproduct. One alternative process being considered is molten oxide electrolysis, MOE. In MOE, Fe2O3 is heated to approximately 1600 degrees Celsius and dissolved in a liquid oxide electrolyte such as calcium oxide, Cal. Fe is formed at the cathode and oxygen gas, O2G, is formed at the inert anode. The inert anode needs to be highly stable and corrosion resistant. Materials being considered for the anode include platinum, PT, iridium, IR, ceramic metal oxides. Question 7a is a classic example of a multi-layered industrial logic problem. To answer it, you must satisfy three conflicting demands simultaneously. Still meeting society's needs. The industrial output must remain high, 1.9 billion tons. Necessary requirement. You must identify the physical or energetic cost of the new technology. Have a positive impact. The environmental benefit must be real, not just shifted elsewhere. Students, if you look at the table in the question stem, you might think we've found a free lunch, a way to make steel with zero emissions. But in science and engineering, there is no such thing as a free lunch. Reducing direct emissions always comes with a cost. Look at the data. To get that zero CO2 at the plant, you must pay a massive energy price. The MOE process demands 14,400 mJ of electricity per ton. That's nearly 17 times the energy used by a traditional blast furnace. This is the necessary requirement you must identify in your answer. Nature's laws dictate that this energy must come from somewhere. To have a positive impact while meeting society's needs for 1.9 billion tons of steel, we cannot ignore this energy bill. Therefore, the only way this lunch becomes responsible is if the energy is paid for by renewable sources. If we use fossil fuels to generate that 14,400 mJ, the CO2 isn't eliminated, it's just being emitted by a different chimney. The half-truth trap. 53% didn't get any mark. 32% of students got only 1 mark because they mentioned electricity, but didn't specify its source, renewables. The vague environmentalist trap. Saying it's better for the earth earns 0 marks. You must use the data, 14,400 mJ, to justify your answer. The anode distraction. Some students focused on the cost of platinum or iridium. While scientifically true, it doesn't address the primary impact requirement related to energy and emissions. The examiners aren't testing your ability to read 0 kilograms of CO2. They are testing your ability to see the 14,400 mJ and realize that much energy needs a sustainable source to truly be responsible production. Give them this formula to memorize. Observation from data, plus logical limitation, plus the renewable solution equals 2 marks. Observation: MOE has a very high energy demand, 14,400 mJ a ton. Limitation: high energy demand usually leads to high indirect CO2 emissions. Solution: this electricity must be generated via renewables to ensure a net positive impact. Goal: Mark 1, acknowledging the energy reality. To meet society's vast needs for steel, the MOE process must operate at an industrial scale. However, the data in the table shows that MOE requires a staggering 14,400 mJ of electricity per ton, nearly 17 times the energy input of a blast furnace. Mechanism: Mark 2, the critical link to sustainability. Therefore, the necessary requirement for a positive impact is that this massive electrical demand must be met by renewable energy sources. If the electricity is generated from fossil fuels, the indirect emissions from the power grid would negate the CO2 benefits at the plant. Evaluate the MOE and the blast furnace processes with respect to green chemistry principles. Refer to item 26.2 of the data book, the information on pages 36 and 37, and content you have learnt in VCE chemistry in your response. Your response must include 2 relevant green chemistry principles and compare both methods against each principle. Describe 1 ethical factor that is important to the challenge of producing steel to meet global needs. Include a concluding statement that is consistent with your evaluation. 6 marks. Command words analysis. Evaluate: this is more than just stating facts. You must weigh the pros and cons and provide a justified judgment. Compare both methods. You must mention both the MOE and the blast furnace for each point. Failing to mention one results in a loss of marks. Refer to item 26.2. You must use the exact names and definitions of the green chemistry principles, GCP, provided in your data book. The 6-mark scoring checklist. White heavy checkmark marks 1 and 2. Identify GCP 1 plus compare both methods with evidence. White heavy checkmark marks 3 and 4. Identify GCP 2 plus compare both methods with evidence. White heavy checkmark mark 5. Describe 1 ethical factor, global context. White heavy checkmark mark 6. Concluding statement, must be consistent with your evidence. Now, let's look at the data provided in the table and see how it fits into the green chemistry principles we find in our data book. When we evaluate these 2 processes, we aren't just looking for better or worse, we are looking for evidence to support specific scientific criteria. First, consider prevention of waste. If you look at the CO2 emissions column, the blast furnace is a massive source of waste, releasing 1,600 kilograms of CO2 for every single ton of steel. According to the GCP definition in table, it is always better to prevent waste than to treat it. MOE effectively achieves this by shifting the byproduct from a harmful greenhouse gas to useful oxygen gas. Next, we must analyze the design for energy efficiency. This is where students often lose marks because they only look at the temperature. While the blast furnace requires a higher temperature of 2,200 degrees Celsius, its electrical demand is quite low at 850 mJ. In contrast, look at the MOE data. It requires a staggering 14,400 mJ of electricity. This is our no free lunch moment. Nature dictates that to eliminate that CO2 waste, we must pay a massive energy price, nearly 17 times more electricity per ton. As the official comments note, MOE is only truly energy efficient if that 14,400 mJ is sourced from renewables. If we use fossil fuels to generate that much power, the process fails this principle entirely. Finally, look at atom economy. Although the math isn't required if your logic is sound, the MOE process is more efficient here too. Because O2 has a lower molar mass than CO2, a higher percentage of your starting reactant mass ends up in your final product, the ion. GCP1, Prevention of Waste. Evidence. Traditional steelmaking produces 1,600 kilograms of CO2 per ton. MOE produces no direct CO2, only O2. Logic. CO2 is a harmful waste with little industrial use, while O2 is less harmful and can be captured for use. GCP2, Energy Efficiency. There is no such thing as a free lunch. Data. MOE requires 14,400 mJ of electricity, 17 times more than the blast furnace, 850 mJ. Logic. Reducing direct emissions has an energy price. MOE is only energy efficient if the electricity is sourced from renewables. Otherwise, it just moves the pollution to the power grid. Ethical factor, global equity. Challenge. Advanced renewable infrastructure is not globally accessible. Developing nations may struggle to transition, leading to economic disadvantages or job losses. GCP1, Waste Prevention. One relevant principle is the prevention of wastes. The traditional blast furnace produces 1,600 kilograms of CO2 per ton of steel as a harmful waste, whereas the MOE process generates O2, which is a non-harmful byproduct with potential industrial uses. GCP2, Energy Efficiency. Another principle is design for energy efficiency. While MOE operates at a lower temperature, 1,600 degrees Celsius versus 2,200 degrees Celsius, it requires significantly more electrical energy, 14,400 mJ a ton, than the blast furnace, 850 mJ a ton. MOE is only efficient if this energy comes from renewable sources. Ethical factor. An ethical factor is the global accessibility of technology. Transitioning to MOE requires advanced renewable grids, which may not be accessible in all regions, potentially disadvantaging producers in lower-income countries. Conclusion. In conclusion, while MOE is superior for waste prevention, its overall sustainability depends entirely on the availability of renewable energy to meet its high electrical demand. Question 7a, 2 marks the no free lunch trade-off. Necessary requirement. Mo's 14,400 mJ per ton electricity demand, 17 times a blast furnace, must be met by renewables, otherwise emissions are just shifted to the grid. Common trap, 53% scored 0, vague better for the earth answers fail, you must cite the data. Question 7b, 6 marks evaluating both processes. GCP1 Waste Prevention. Blast furnace emits 1,600 kilograms CO per ton, while MOE produces only harmless O2. GCP2 Energy Efficiency. MOE runs cooler, 1,600 degrees Celsius vs. 2,200 degrees Celsius, but needs far more electricity, green only if renewable. Ethical factor. Global equity. Renewable infrastructure is not equally accessible to all nations. Conclusion. MOE is superior for waste prevention, but its overall sustainability depends entirely on renewable energy. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.